Picture this. You train your machine learning model, you check the metrics, and the accuracy is like 92%.
Which is, a solid number.
Right. Totally solid. You're feeling really good about the architecture. So you decide to rerun the exact same pipeline just to verify your results. You don't change a single line of code. You hit run. And suddenly the accuracy jumps to 97%.
Oh, man. That's a terrifying moment in engineering.
It really is. What just happened? I mean, the culprit isn't some miraculous improvement in your neural network. You are actually looking at one of the most dangerous silent failures in machine learning. Your dataset was modified silently during preprocessing, all because of, well, the underlying mechanics of Python's object model. Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry-ready and apply your knowledge to real industry projects.
Yeah, we are taking a deep dive today into the underlying Python concepts that cause these invisible pipeline-destroying bugs. We're dealing with an ecosystem where memory management completely dictates how data flows.
Exactly. And by understanding the why beneath the code, you gain the ability to completely avoid the silent mutations that lead to data leakage and fabricated metrics.
Right. It's all about building that intuition.
So the mission of today's deep dive is really to reconstruct your mental model of data management. Because to understand how your data can mutate without explicit instructions, we have to kind of unlearn a fundamental assumption.
You mean the classic bucket analogy?
Yes. Many of us are taught early on that variables are like little buckets or containers holding our data. You picture a bucket labeled X with the number 5 sitting inside it.
And honestly, that bucket analogy is the root cause of countless bugs in machine learning pipelines.
It really is.
The core insight you really have to internalize today is that Python variables do not store data. They just store references to objects in memory.
So the variable is essentially just a pointer.
Exactly. It just points to a location.
I find the stack versus heap model from our sources to be the perfect way to visualize this. Imagine your computer's memory is divided into 2 distinct areas. The stack is like your desk. It's fast, it's small, and it's right in front of you. On your desk, you have a pad of sticky notes.
I love this analogy. And the heap is, the warehouse down the street.
Yeah, exactly. The heap is a massive warehouse down the street. It's enormous, and it dynamically allocates space as you need it. So when you write a line of code like equals a list of 1, 2, 3, you aren't placing that list of numbers on your desk.
Right. They take up way too much room for the desk.
Precisely. You are placing that list into a box in the giant warehouse. Then you write a sticky note on your desk, you label it A, and you jot down the warehouse address of that specific box.
And that architecture right there completely dictates the behavior of assignment operations in Python. So when you write your next line of code, say B equals A, Python optimizes for speed and memory.
It doesn't want to do extra work.
Exactly. It does not go down to the warehouse, build a brand new box, and carefully copy the numbers 1, 2, and 3 into it. That's just too slow. It simply writes a second sticky note on your desk, labels it B, and copies the memory address from the first sticky note.
Wow. So you now have 2 distinct variables pointing to the exact same location in the heap.
You really do. And this is where the illusion breaks and where we start seeing those pipeline failures you mentioned at the start.
Wait, so if I decide to modify B by appending the number 4 to the list, doesn't it stay the same since they're different variable names?
You would think so, right? But no, since they both point to the same warehouse box, if you append a 4 to B, a B will instantly output 1, 2, 3, 4 as well.
Oh, man. So the names on the sticky notes are totally irrelevant.
Completely irrelevant, because they point to the identical heap object. Modifying the contents of that warehouse box through one reference alters what every single other reference sees.
That is wild. And you can actually verify this in your own code using Python's built-in EAD function. Like printing the ID of A and the ID of B will output the exact same integer.
Right, which proves they literally share a memory address.
Yeah.
So tying this back to your opening scenario, let's look at the real-world machine learning application here.
The data leakage issue.
Exactly. A very common pattern for beginners is to write test data equals train data, because they want to keep a pristine copy of their training set before they start applying transformations.
Oh, I have done that so many times.
Right. And then later in the script, they run test data equals preprocess of test data. They might apply a scalar to normalize the features or something like that.
And because of that shared reference, the original training data is silently modified.
Yep. It gets normalized using the statistics of the test set, which completely corrupts it.
And for those newer to machine learning concepts, this is exactly what creates that phenomenon called data leakage. Think of training a model like a student studying for an exam.
Oh, that's a great way to think about it.
Thanks. So the training data is the textbook, and the test data is the final exam. The goal is to see if the student can generalize what they learn to new, unseen questions.
Right, they should know the test questions in advance.
Exactly. Data leakage is like accidentally leaving the final exam answer key tucked inside the textbook.
Yeah.
The student studies the answers, takes the test, and gets a 97%.
It looks like pure genius, but it's actually just cheating.
Yeah, exactly. And when you deploy that model in the real world, where it obviously doesn't have the answers in advance, it completely fails.
And that fake 97% accuracy metric is born entirely from a shared memory reference.
Yeah.
So to protect our pipelines, we really have to know how to accurately audit our memory.
Meaning we need to know if two variables are sharing a warehouse box, or if they just happen to contain identical values.
Exactly, which introduces a professional rule regarding identity versus equality. We basically rely on two operators here, the double equal sign and the keyword is.
So the double equal sign checks for equality. It essentially asks, do these two boxes in the warehouse have identical contents?
Right. And the is operator checks for identity. It asks, are these two sticky notes pointing to literally the exact same box?
Wait, I need to push back on this a little bit because I actually ran into a severe debugging nightmare with the is operator early in my career.
Oh no, let me guess. It had to do with numbers.
Yes. I was working with some data batch counters. I had A equals 10 and B equals 10. When I evaluated A is B, Python returned true. They were sharing the same box.
Yep, standard behavior so far.
Right. But later my batch size increased. So I had A equals 1,000 and B equals 1,000. And when I evaluated A as B this time, it returned false. How does that make any sense? Python treated the small numbers as the same object, but the large numbers as different objects.
Yeah, you fell right into the interning trap. It's a classic Python gotcha.
The interning trap, what is that?
So CPython, which is the standard implementation of Python, includes a specific memory optimization feature. It recognizes that developers use small integers constantly.
Like for loop counters and array indexing.
Exactly, basic arithmetic. To save the overhead of constantly creating and destroying boxes for these common numbers, Python actually pre-allocates an array of integer objects from -5 up to 256 the moment you start your environment.
Oh, wow. So when I assign 10 to a variable, Python doesn't create a new box.
No, it just points your sticky note to the permanent 10 box it already built. But 1,000 falls outside that pre-allocated range. It's not cached. So Python dynamically allocates two separate memory locations for your two 1,000s.
Man, that frugal memory management behind the scenes makes the is operator incredibly dangerous for value comparison.
It really does.
Yeah.
Which leads to the golden engineering rule. Strictly use the double equal sign for comparing numbers, strings, or data structures.
And you only pull out the is operator when checking for none. Right.
Exactly. In Python, none is a guaranteed unique singleton object. There's only ever one. None box in the warehouse, making is turn. None both safe and highly efficient.
Okay, so let's follow this memory management logic to its next phase. We know we can have multiple sticky notes pointing to a single box in the warehouse. What happens when those sticky notes start getting thrown away?
That's where the garbage collector comes in. Every object in the Python heap maintains a hidden reference counter. Think of it as like a digital tally mark attached to the side of the warehouse box.
So if variables A and B both point to a data set, the reference count is 2.
Right, and if you execute del B, you are throwing away that specific sticky note, and the tally drops to 1.
Got it. And when the reference count hits 0?
That signals that absolutely no part of your active program is looking at this box anymore. This triggers the garbage collector, which is an automated background process.
So it sweeps through the heap, permanently deletes the unreferenced object, and frees up the physical RAM.
Exactly, cleans out the warehouse.
And the mechanics of this garbage collector are incredibly critical for machine learning engineers. I mean, we aren't dealing with small lists of numbers. We're dealing with multi-gigabyte arrays representing high-resolution images or massive text embeddings.
Oh, absolutely. The scale changes everything.
Right, so picture a common scenario. You are running a training loop over hundreds of epochs. Inside the loop, you might accidentally append a large tensor to a tracking list that sits outside the loop, maybe just to monitor the loss.
I see where this is going.
Yeah, you only intended to save the single float value of the loss, but you accidentally saved the whole tensor object. Because that outer list holds a valid reference, the reference count for those gigabyte-sized tensors never drops to zero.
So the garbage collector is entirely blocked from cleaning them up.
Exactly. The memory consumption just stacks with every iteration of the loop.
And you end up with a massive memory leak.
Boom. The warehouse hits maximum capacity, your server runs out of RAM, and your script crashes midway through a 3-day training job.
It's painful. Managing your references isn't just about avoiding mutation, it's actually about keeping your infrastructure alive.
Totally. So a seemingly obvious solution to all these shared memory complications is to simply stop sharing, right? Like, just use the .copy command.
Yeah, developers often discover Python's .copy method and just start applying it absolutely everywhere.
But treating .copy as a universal fix actually introduces a much more insidious bug, doesn't it?
It absolutely does.
Yeah.
We really have to separate the concept of a shallow copy from a deep copy.
Okay, walk us through that.
Consider a configuration dictionary used to set up a neural network. You have your config equals a dictionary with a learning rate of 0.01 and a key for layers containing a list of 64 and 32.
So the dictionary contains a simple float and a nested list representing the hidden layers.
Right. If you create a new variable using new config equals config.copy, you are executing a shallow copy.
And a shallow copy builds a brand new warehouse box for the outermost layer, which is the dictionary itself.
Exactly. So if I modify the learning rate of my new config from 0.01 to 0.1, the original configuration is perfectly safe. They are completely independent at the top level.
Okay, so far so good. But the layers are stored in a nested list.
And that is the trap. A shallow copy does not duplicate nested structures. It simply copies the memory references, the sticky notes, for anything inside the dictionary.
Ah, I see. So both the old config and the new config contain pointers to the exact same list of layers.
You got it. If I alter the first layer new config from 64 to 128, the original config is instantly mutated.
I actually think of this like copying a recipe card. Let's say I borrow your famous chili recipe. I photocopy the physical card, creating a shallow copy.
Okay, I like this analogy.
Thanks. So I can cross out bake at 300 degrees and write 400 degrees on my copy, and your original card remains untouched.
Because we have separate physical cards.
Right. But down in the ingredients, both our cards say, use the secret sauce stored in the main fridge. We have different cards, but they point to the exact same physical jar of sauce.
Right, the shared resource.
Exactly. If I go to the fridge and pour an extra cup of salt into that jar for my batch, I have fundamentally ruined your chili as well, because you are pulling from the same mutated source.
That's perfectly explained. And the mechanism to avoid the shared jar of sauce in code is the deep copy.
So how do we do that?
You must import copy from the standard library and execute copy.deepcopy. Deep copy recursively traverses your entire object hierarchy.
So it looks at the dictionary and builds a new box.
Yes, and then it looks at the nested list and builds a brand new box for that too. It ensures total memory independence from top to bottom.
That is super helpful. Standard Python rules obviously require a lot of vigilance, but as machine learning engineers, we spend the majority of our time inside external libraries like NumPy and Pandas.
Oh yeah, data frames and mathematical arrays all day long.
Exactly. So do these memory rules still apply there? I feel like it's crucial to understand how these tools handle memory.
They actually apply even more aggressively in NumPy. NumPy is fundamentally engineered to minimize memory overhead to allow really fast matrix multiplication.
So it shares memory even more.
Yes. When you create a NumPy array A, and you take a slice of it, say B equals a slice from 0 to 5, NumPy does not allocate new memory for those 5 elements. It creates what is called a view.
A view, like a window.
Exactly. A view is simply a new metadata header. It tells Python, I'm looking at the same continuous block of C memory as the original array. I'm just restricting my window to the first 5 elements.
So if you modify an element in the view, like changing B index 0 to 99, you are literally overwriting the underlying C memory block.
Correct. The original array A instantly reflects the change. NumPy assumes that duplicating millions of floats is just way too computationally expensive, so it defaults to shared views unless you explicitly invoke .copy.
Let me bring up a real machine learning bug scenario to show how this view mechanic can completely destroy cross-validation loops.
Oh, this is a great example.
So imagine you write a poorly written custom function to scale your data. Instead of returning a new array, your code modifies the input feature directly in place, like x:0 equals x:0 times 2.
A classic in-place transformer mistake.
Right. So during fold 1 of cross-validation, your scaler alters the shared NumPy memory. When fold 2 begins, it is not receiving the raw original dataset. It is receiving data that has already been multiplied by 2.
Because the memory was already mutated.
Exactly. By fold 5, your data set is just compounded garbage. But here is the really terrifying part. Your model might actually latch onto the artificial patterns created by the compounded scaling,
Wow, yeah, so your evaluation metrics will look fantastic.
totally inflating the performance metrics.
Yeah.
The model has learned the geometry of your bug, not the geometry of the real data.
And this memory model dictates how entire frameworks are built. Scikit-learn, for instance, is explicitly engineered so that its transformations return entirely new arrays by default.
To avoid that exact mutation bug.
Exactly. It sacrifices some memory efficiency to guarantee functional purity, isolating your cross-validation folds. But as you move into deep learning with frameworks like PyTorch, the philosophy shifts again.
Because of GPU memory limits, right?
Exactly. PyTorch operates on GPUs, where video RAM is incredibly scarce and expensive. Allocating a new 4 GB tensor for every single mathematical operation is just impossible.
Right, you'd run out of memory instantly.
So PyTorch actually allows in-place operations, which are visually flagged with a trailing underscore, such as add or mul.
Oh, I've seen those. That underscore is basically PyTorch's hazard light. It tells the engineer, I am modifying this tensor directly in the VRAM without making a copy.
Spot on. Using an in-place operation saves memory, but it introduces massive risks to the computation graph.
Because it needs to calculate gradients.
Right. PyTorch relies on tracking every operation you perform so it can calculate the gradients backward during training. If you mutate a tensor in place after it has been registered in the computation graph, PyTorch loses the original value needed for the derivative math.
That sounds catastrophic.
It is. Best case scenario, PyTorch throws a runtime error and stops you. Worst case scenario, the backpropagation quietly computes incorrect gradients, and your neural network simply fails to converge.
Wow. We have really mapped out the entire terrain today. From the stack and the heap to the invisible reference counters, the dangers of shallow copies, and those in-place operations threatening our GPU memory.
It's a lot to take in, but it's so fundamental.
It really is. So let's synthesize this into a concrete professional machine learning engineering checklist for you. First, track your data lineage. Always know exactly which variables point to shared memory and which are independent copies.
Second, avoid in-place mutations in your data pipelines. Treat your raw data sets as immutable objects.
Third, whenever you slice a NumPy array, operate under the assumption that you are creating a shared memory view, not a duplicate.
Fourth, before running a critical pipeline, check your train and test sets with the edit function to definitively prove they occupy different memory addresses.
And fifth, when working with nested configurations or layered data structures, never trust a shallow copy. Default to copy.deepcopy.
That is a solid checklist.
Thanks. I actually have a micro exercise for you to try immediately after this deep dive. Open up a Python script. Create a nested dictionary representing a model configuration.
Break it on purpose.
Exactly. Try a shallow copy and intentionally break the original by modifying a nested list inside the copy. Observe the mutation. Then fix it with deep copy and verify the isolation.
And for a real challenge, you can simulate a dummy training and testing dataset, introduce a silent mutation bug using a NumPy view, detect the shared memory using the id function, and then refactor the code so the pipeline is secure.
Interacting directly with the memory architecture is really the only way to solidify the mental model. Reading about a bug is helpful, but engineering the bug yourself and fixing it is what builds true intuition.
Hands-on practice is everything.
And that hands-on approach is exactly where we're heading next. I am super excited to announce that our next lecture is the Mutability Deep Dive plus Breaking Real Pipeline.
Well, that's going to be a good one.
Yeah, we will be intentionally breaking OS Automator, tracing these exact mutation bugs as they cascade through a complex multi-file system, and implementing architectural fixes like true ML engineers.
I cannot wait for that. As we wrap up today, though, consider the underlying paradox of everything we have discussed. Python's reference model is responsible for a massive percentage of our silent, pipeline-destroying bugs.
We spend hours debugging shared state.
Exactly. Yet, without this system of shared references, our machines would instantly run out of memory trying to duplicate gigabytes of data for every simple assignment.
It's a necessary evil.
It is, which raises a really compelling architectural question for you to mull over. Knowing the risks of mutable state, is there a pragmatic way to write an entire machine learning pipeline that's completely immutable from end to end without exhausting our hardware resources?
That is a fascinating problem, something for you to think about the next time you stare at an accuracy metric that seems just a little too good to be true. Until next time.